Okay, got another exam walkthrough for you. This one is from June 2023, Unit 5, Physics. So the first question says, a nucleus of radium 187 decays to a nucleus of osmium by emitting a beta minus particle, and it says complete the nuclear equation. So it's a very simple question. So we know that the beta particle, it's a beta particle with a negative charge, so it's going to be -1 over here, and we have no protons or neutrons, so it's going to be 0 right here. And then we're going to balance it all out, so we're going to put 187 here, and then to balance the lower part of this equation, we're going to be putting a 76 here, so pretty simple. And then it says the energy released in the decay is 2.6 kilo electron volts. You may assume that in this case that the beta particle receives all the energy. So we have all of this energy going to the beta particle, and it says calculate the speed of the particle, beta particle. So all of this energy goes to beta particle as the kinetic energy of beta particle. We are making that assumption. So we're going to say 2.6 times 10 to the raised power of 3 times 1.6 times 10 to the raised power of -19. So basically I've converted the energy into joules. Now I can apply the formula. The kinetic energy is equals to half mv square, and v is equals to square root 2 kinetic energy over m. So I can just plug the values in then. 2 times 2.6 times 10 to the raised power of 3 times 1.6 times 10 to the raised power of -19 divided by the mass of a beta particle is 9.11 times 10 to the raised power of -31. That's going to give you an answer of 3.0 times 10 to the raised power of 7 meter per second. Pretty simple. Okay, next question is another very interesting question. This is about how a cloud chamber works. So we have a cloud chamber is used to show the tracks of alpha and beta particles. Then it says these particles ionize the air as they pass through the chamber. They're going to be forming these droplets that will be forming on the ions, and then we'll have visible tracks. Okay, and then it says the alpha particle tracks are much thicker and much straight, whereas beta particles are much thinner and much twisted. Okay, so we have to explain these observations. So first of all, you want to understand that how it works is like this. When you ionize the air, you get the tracks. Okay, so you're going to be ionizing the air, and based on that, you're going to get the tracks. Now, that means that the thickness of this tracks is related to the ionizing power. Now, the more you will ionize, the more the tracks will become thicker. Now, we know the alpha particle has a higher ionizing power than beta particle, and that's the reason why the track for the alpha particle is thicker, and the track for the beta particle is much more thinner. Okay, that's going to give you 1 point, and this is going to give you 1 point. Now, the next thing you want to explain. So I've explained the first thing, why this is thick and this is thin. Next, I want to explain why alpha is going straight and why the beta is becoming twisted. So we have a lot of air molecules surrounding us, okay? And then we have our beta particles here and our alpha particles. Now, alpha particles, now remember, the path of beta and alpha is related to their mass, and what's going to happen is we know that beta particles are lighter in mass, so they're going to get knocked around by these air molecules, and that's why they give you that zigzag track. But alpha particles are much heavier, so they're not going to be knocked around by the air molecules, and because of that, their path will be much more straighter. So you can write the beta is lighter and the alpha is heavier in mass, And that's why the beta gets knocked around by the air particles, and it gives you that twisted track, and on the other hand, alpha doesn't get knocked around. Okay, so that's the answer. I will show you the mark scheme and the examiner report for this, so you can just go through that. Alright, next it says a nucleus of thorium-230 is unstable and decays to a nucleus of radium-226 by emitting an alpha particle. We have been given the masses, and says determine the energy joules that is released when a nucleus of thorium-230 emits an alpha particle. So we know what to do here. We have to find the change in mass. That's going to be 230.0331 minus 226.0254 plus 4.0026. That's going to give me the change in mass. So my calculator is giving me 5.01 times 10 to the power of minus 3U. Now we know U is the atomic unified mass. So we're going to plug the value in for that, 1.66 times 10 to the power of minus 27. That's going to give us the mass in kg, and that's going to be, so I made a mistake, the calculator, just 5.1. Okay, so you'll get the answer at 8.47 times 10 to the power of minus 30 kg, and then you're going to plug it into E is equals to m, change in mc squared, so you're going to get 8.47 times 10 to the power of minus 30 times 3 times 10 to the power of 8 squared, and that's going to give you 7.62 times 10 to the power of minus 13 joules. Okay, I made a little bit of a mistake here, but this is a pretty standard question, and you should be able to get all the marks till now. Okay, next question. Determine the time taken in years for 90% of thorium-230 in the sample to decay to radium-226. So let's find, so we know that we have to find that initially we have 100% of the thorium, and then 90% of it goes away, so we have 10% left, right? So this is the N and this is the T. So initially you have 100, and then as you decay, at a point you're going to get 10% of the initial value left, and that is time T. So we have to find that value out. So we can use the formula N is equals to N naught E minus lambda T. Now lambda is equals to ln2 over half-life. Give me a sec. Over the half-life. So ln2 over 75,400. That's the lambda value. You don't have to convert it. We want the final answer in years. And then what I'm going to do is I'm going to say that my initial value was N naught. And now what I have left is 10% of N naught. 10% of what I initially had. So I'm going to put 0.1. Or you can even put here 10. You can just write initially it was 100. And then now you have 10 left. So 90% is gone. That's going to give the same answer either way. And then you can put minus ln2 75,400 T. Okay, so you can divide the other side. So 10 divided by 100 is equals to E minus ln2 75,400 T. Take ln on both sides. You're going to get ln 0.1 is equals to minus ln2 75,400 T, and then you can just make T the subject, so you're going to get ln 0.1 times 75,400 divided by minus ln2. So your final answer will be 2.5 times 10 to the power of 5 years.